Here we are having a problem. A graph is given to you. So it is a velocity time graph. So it is marked in along the x-axis we have seconds, and the unit in the y-axis is meter per second. 6 meter per second, 4 meter per second, 2 and 4, 6. Okay. Now, what is the velocity? So we have three questions. What is the first question? What is the velocity at t equal to 3 seconds? What is the acceleration at t equal to 2 seconds? And what is the displacement across t equal to 3 seconds and 6 seconds? Remember, t equal to 3 seconds. So always, so the data that is given to you, always try to see where the graph is for this data. T equal to 3 seconds, so we have got this straight line. T equal to 2 seconds, we have got this tip. T is 3 seconds and 6 seconds, T 3 seconds and 6 seconds. So always try to drop the perpendiculars to the graph. So let's address the first question. The first question is, we are supposed to find what is the velocity at t equal to 3 seconds. For finding the velocity at t equal to 3 seconds, we know that 3 is between 2 and 3, 2 and 4. So we take a point and we drop the perpendicular to the graph. And we know that where the graph, okay, so where the graph lies for the y-axis corresponding to this 3, that will be the answer, because that represents the velocity at 3. And we know that the straight line, it's already given in the question that it is 4. So just by looking at the graph, we will have the answer. The velocity at t equal to 3 seconds is 4 meter per second. Now we have been asked, what is the acceleration at 2 seconds? For finding the acceleration at 2 seconds, we note the formula for acceleration, that is v minus u by t, final velocity minus initial velocity by time. So the final velocity is the velocity at t, at t equal to 2. So that is 4 meter per second, and u is initial velocity, that is at 0. So 4 minus 0 by 2 seconds. So that is 2. So we'll have 2 meter per second square. And then we are supposed to find the displacement between 3 and 6. For finding the displacement between 3 and 6, remember, when a velocity time graph is given, the area under the graph, so we have to note 3 and 6, then we have to shade all the area under the graph between 3 and 6. That's exactly what we have done here. So if you look here, so here we have got, so here we are having two figures. One is a rectangle and other is a trapezium. So we will be breaking down into two components and we will be individually evaluating the areas. So the first area is 4 minus 3. 4 minus 3, that is breadth into length. Breadth is 4 minus 3 into 4. That is the length. So that will be the area of the rectangle. Then we will have the area of the trapezium. Half times, there is a 6 here. 6 minus 4, that will be 2. Then 4, so 6 and 4, the two opposite parallel sides, we sum it. So finally we will be getting the answer 14 meters. So that will be corresponding to the displacement between 4 and 6. Now let's discuss about equations of motion. So whatever formula we are going to discuss, it is applicable only when we have constant acceleration that happens along a straight line. If you have a curved motion or if you have a non-uniform acceleration, these formulas are not at all applicable. So this is the condition in which these formulas work. So we are having three formulas. So the first formula is simply v equals u plus at. This is obtained by rearranging a equals v minus u by t. So v, final velocity, u is initial velocity, a is for acceleration and t is for time. And second formula is the displacement. S here is for displacement. S equals u is initial velocity, t is time, half a is acceleration, t square. S equals ut plus half at square. Then we have the final formula, that is 2as equals v square minus u square. Here a is acceleration as usual. Then s is for displacement. 2as equals final velocity square minus initial velocity square. So here there is time. Of these three formulas, in the third formula we don't see time. So this is a time independent formula and these two formulas are time dependent formulas. So uniform circular motion. So let's consider a body which is moving in a circular path. So once it is moving in a circular path, we know that the circle has got radius r. So we have uniform circular motion. So uniform speed, okay. So uniform circular motion means the speed is always constant for this motion. But the direction, so we specify the direction as tangents. So these lines, arrows are tangents. So this is for when the body is here, it is having a direction this. So when the body is here, it is having a direction, that is a tangent. So at each and every point, the direction is given, the direction keeps on changing. The direction at this point and the direction at this point are different. So the direction overall changes, but the speed is constant. So this is what you mean by uniform circular motion. So since the direction keeps on changing, we say that the velocity changes for uniform circular motion, but the speed is fixed. And by the definition of the speed, we can have the distance covered by time taken. For the total, the distance covered is equal to the circumference of the circle, and that is 2 pi r divided by the time, the total time taken for revolution. That will give us a definition for speed or uniform speed for a circular motion. And now, when a body is released, let's say that the body is moving in a circular path and suddenly it is released. We know that if it is suddenly released, the body has to travel in a tangential path, and that will be like this. Let's say that the body is released from this point, it moves tangential. So in this unique straight line direction, the body goes. So this is a property of uniform circular motion.